This video introduced the paper SINDER, Repairing Singular Defects of DINOv2, published on ECCV 2024. DINOv2 is a powerful vision foundation model that is widely used nowadays. The video below is the visualization of the DINOv2 feature of this running dog. Notice that there are some defective pixels flickering in the frames. These defects have been observed in previous works such as vision transformers need registers. One characteristic of the defective tokens is their high norms shown in the video here. These defects hurts the feature quality of the model and may lead to undesirable performances on downstream tasks. Our paper can repair these defective tokens as shown in the feature maps. It is very clear that the defective tokens are disappeared, and we have spatially smoothed and semantically coherent feature maps. We observed that the defective tokens across different images share a common direction. Specifically, the average pairwise angle between defects within each image is 3.1 degrees, and the average pairwise angle between defects across images is 5.5 degrees. This shows the directions of defective tokens are nearly input image agnostic, and suggests that defective tokens may be caused by defects in model parameters. Motivated by this, the first objective of our work is to predict the direction of defective tokens from model parameters. To make the analysis tractable, we use two assumptions. The first one is to only consider the single token case. This will simplify the analysis of tension, since it ignores the interaction among tokens. The second assumption is to study the linear approximation of the network, which enables the usage of tools in linear algebra, such as SVD. We start with the linear approximation of the attention block in the vision transformer. Note that in the single token case, the multi-head attention can be represented by two matrices, the value matrix and the output projection. In the end, the attention block is approximated as a linear operation AX plus B. For the nonlinear MLP layer in the MLP block, we use the least square to approximate it. In the end, the MLP block is approximated as a linear operation CX plus D. Combining the linearized attention and MLP, and by composing multiple layers from layer 0 to layer I, we can obtain matrix GI to represent the transformation on input tokens for these layers. And we define the leading left singular vector of GI to be the singular defect direction for layer I. Now we visualize the predicted singular defect directions. This violin plot is the angles between the predicted singular defect direction and patch tokens of each layer. We can see that most angles concentrate around 90 degrees, while some outliers are close to our predicted singular defect direction. And these outliers are exactly those defective tokens, as shown by the figures in the last two rows. We proposed an algorithm to repair the defective tokens. The principle of the algorithm is to modify as few parameters as possible to retain the original feature quality. We use the predicted singular defect direction to find defective tokens in each layer, and we use neighbor loss to learn a smooth feature map on the defective tokens. We tested our repaired DINOv2 model on unsupervised segmentation tasks and got improved results using both cause and stego algorithms. Our repaired model also demonstrates superior performance on the supervised segmentation and supervised depth estimation tasks. These results shows that SINDER improves the feature quality of patch tokens. We also tested the classification on ImageNet1K to demonstrate that our algorithm repairs the defective patch tokens while maintaining the classification tokens quality. Our algorithm is extremely efficient. Compared with DINOv2 register, SINDER uses 4,000 times fewer images and 4,000 times fewer learnable parameters. These leads to 3,000 times more efficient training, measured by GPU hours. Our code and checkpoints are released in GitHub. Thank you very much.